In this module, we are going to explain about the distributed lag models. So far we explained about the regression model in which the dependent variable depends upon the current value of the model. So we specified is like this: yt equal to alpha plus beta xt plus ut. That is, yt depends upon xt. But there are situations in which the lagged values of both explanatory variable as well as the dependent variable can have an influence on the regression model or on the models. These types of the influence of the lag on the regression model and its estimation methods are explained in this chapter. First, we will see what is a distributed lag model. If the regression model includes not only the current but also the lagged values of the explanatory variable, the x, it is called the distributed lag model. That is, if the regression model includes not only the current but also the lagged values of the explanatory variable, it is called the distributed lag models. That is, yt equal to alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 plus ut. Now here yt is a function of the lagged values of the xt minus 1 and xt minus 2. Here xt minus 1 and xt minus 2 are the lagged values of xt. Therefore, these types of models are known as the distributed lag model. There exists another model known as autoregressive model. If the model includes one or more lagged values of the dependent variable among its explanatory variables, it is called autoregressive model. That is, yt equal to alpha plus beta xt plus gamma yt minus 1 plus ut. Here, yt minus 1, this is the lagged value of the dependent variable, that is yt. And if a regression model includes the lagged values of dependent variable as explanatory variable or independent variable in a model, that types of models are known as autoregressive models. And this models is also known as dynamic model, since they portray the time path of the dependent variable in relation to the time path is explained in this model. That is, the influence of the dependent variables time path in the regression model is specified through the autoregressive model. Therefore, this is also known as dynamic models. The role of time or lag in economics is explained in the following 8th section. Some of the examples are given to make it more clear. First one is the consumption function. Suppose a person received a salary increase of 2000 in annual pay. That is, this is an increase in his annual pay. It is about $2,000. And suppose that this is a permanent increase in the sense that the increase in salary is maintained. This is a permanent increase in the sense that the increase in salary is maintained. That suppose that this increase in $2,000 is permanent. That is, we will get it in every year. What will be the effect of this increase in income on the person's annual consumption expenditure? Here, we want to see the influence of this increase in income on the consumption pattern or on the consumption expenditure of the person. Following such a gain in income, people usually do not rush to spend all the increase immediately. We all know that even if our income or there is an incremental increase in income every year, we won't spend it all in that year itself. We keep a portion of the increased income for saving. Like that, in the first year, he increases the consumption expenditure by $800, and in the second year or in the next year, he increases income by another $600, and third year by $400, and he will save the remaining portion. That is, person's annual consumption expenditure will be increased by $1,800. That is 800 plus 600 plus 400 by the end of the third year. The consumption function can be specified as follows. That is, yt equal to a constant plus 0.4, that is 60%, 40%, and that is the consumption function can be specified as follows. Yt equal to constant plus 0.4 xt plus 0.3 xt minus 1 plus 0.2 xt minus 2 plus ut. That is, likewise, we can specify a model to show the changes in the consumption pattern over the years due to an increase in the income of a person. Here, 0.4 means 40% of the total income increase in income is used for consumption in the first year, then 30% in the second year, and 40% and 20% in the third year. Whereas the consumption expenditure exceeds the income. And this equation shows that the effect of an increase in income of rupees $2,000 is spread or distributed over a period of 3 years. That is, the effect of increase in income is spread over a period of 3 years model, such as one are therefore called the distributed lag model. That is, the effects of increase in income is spread over 3 years, and therefore this model is known as distributed lag model because the effect of a given cause is spread over a number of time period. That the effect of a given cause, that is increase in income, is spread over a number of period. This can be specified as in the following figure. That is, suppose in the figure, in the T1 period he will increase the consumption by 800, then T2 period 600, and T3 period 400. That is, total increase in income, increase in consumption is about $1,800. And more generally we can write the equation as follows. For an infinite lag model, for a finite lag model, we can specify the above model, or we can generalize the above model as follows: yt equal to alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 plus beta k xt minus k plus ut, which is a distributed lag model with finite lag of k time period. The coefficient beta 0 is known as short trend or impact multiplier because it gives the change in the mean value of y following unit change in x. Here, this beta 0 is the short trend or the impact multiplier. It shows the short trend impact. If the change in x is maintained at the same level after that period, then beta 0 plus beta 1 gives the change in the mean value of in the next period, then beta 0 plus beta 1, beta 0 plus beta 1 plus beta 2 in the next period, and so on. And these partial sums are called the interim or intermediate multiplier. That is, here beta 0 plus beta 1 and beta 0 plus beta 1 plus beta 2, these are known as the interim or the intermediate multiplier. And finally, after k period, we obtain sigma of I equal to 0 to beta I, sigma of I equal to 0 to k of beta I equal to beta. That is, the partial sum of all these beta 0 plus beta 1 plus beta 2 plus beta k will be equal to the beta. This is the long run multiplier, which is known as the long run or the total distributed lag multiplier, provided the sum beta exists. Beta I star is defined, or the standardized beta I is defined as beta I by sigma beta I. Here sigma beta I is nothing but the this one, beta 0 plus beta 1 plus beta 2 plus beta k. Then beta I by beta is the standardized beta I. Partial sum of the standardized beta I then gives the proportion of the long run or total impact felt by certain time period. In the consumption regression, we use the short run multiplier, which is nothing but the short run marginal propensity to consume is 0.4, whereas the long run multiplier is 0.4 plus 0.3 plus 0.2, 0. That will be equal to 0.9. This shows that following a dollar increase in income, the consumer will increase his or her level of consumption by about 40% in the year of increase, 30% in the next year, and by another 20% in the following year. The long run impact of an increase of $1 increase is thus 90%. If we divide beta I by 0.9, we obtain 44%, 33%, and 23%, which indicate 44% of the total impact of unit change in X on Y is felt immediately, 77 in the next period, and 100% by the third year. This can be shown as in the following figure. Here, this in the current period, this in the T minus 1, T minus 2, etc. The effect of a unit change in X at time T on the Y at time T and subsequent years. The second example is on the creation of bank money or the demand deposit. Suppose the Federal Reserve System pours $1,000 of new money into the banking system by buying government securities. What will be the total amount of bank money or the demand deposit that will be generated ultimately? Here, if new money is introduced into the banking system, if new supply of money is created in the banking system, what will be its impact on the demand deposit is explained here. Following a fractional reserve system, that is, we have to keep a fraction or the cash reserve ratio. We have to keep the reserve ratio for providing loans and loans, and we have explained it in the credit creation process of the banks. And that means following the fractional reserve system, if you assume that the law requires the banks to keep a 20% reserve backing for the deposits they create, then by the well-known multiplier process, the total amount of their deposit that will be generated will be equivalent to the $100 into 1 by 1 minus 0.8, that is 0. So, and the after keeping the deposits, after keeping the reserves, nearly $5,000 will be created in the form of the demand deposits or overnight. And this process takes time, which can be shown as follows. After keeping 20% in reserve, the first year the bank will provide 800 or to the first customer. Then after that, 640 by keeping in the 20% and reserve. Then likewise, the total demand deposits that can be created will be equal to 5,000. Then third example is the J curve of international economics. The J curve shows the relationship between the trade balance and depreciation of the currency. And this relationship shows that the country's currency due to devaluation initially, following the depreciation of country's currency or due to the devaluation, initially the trade balance deteriorates, but eventually it improves, other things remaining the same. This effect is drawn, that is, following the devaluation, firstly the trade balance will deteriorate, then it will improve. And this shows this will take the time to show its impact on the trade balances. And fourth example is the lag between R&D expenditure and productivity. That is, decision to invest in research and development expenditure and its ultimate payoff in terms of increased productivity involve considerable lag. Actually, several lags as such. The decision to invest in research and development expenditure and its ultimate payoff in terms of increased productivity involve considerable lag. Actually, several lags. That is, we cannot increase the productivity as soon as the investment in research and development. It will take time to get its results after a lag of time after the investment in research and development, or we cannot feel the increase in research and development expenditure on productivity immediately. This is another example. Then another example is the accelerator model of investment. In its simplest form, the acceleration principle of investment theory states that investment is proportional to change in output, that is, IT equal to beta into xt minus 1. Where IT is investment at time t and xt is output at time t and xt minus 1 is output at time t minus 1. That is, investment is proportional to change in output, or it will take time to adjust to the investment. In its simplest form, the acceleration principle of investment theory states that investment is proportional to change in output, that is, it will take time to respond to the investment, or change in output take times to adjust with the investment.